Okay, we've spent our last couple of videos getting ourselves used to this thing we've called the derivative of a function. So we've got our notation sitting right here for f prime of x. I filled in f prime of c in this instance because you might have ended up wondering, the derivative is at its heart a limit, and we've seen already that limits don't always exist. So under what circumstances might it be possible that our function's derivative doesn't exist for a given x value? That's where the c comes in. So I've gathered up the three main ways that might end up happening for us in a handy little list right here. First off, as it turns out, if you can take a derivative, your function has to be continuous at that point. I'm not going to drag you through a proof of the fact, but it is. So anytime you have a discontinuity, be it like a vertical asymptote as we've seen before, or a break in the graph like with our absolute value, stuff that we've seen, back in chapter 1, or even if there's just a hole in the graph, at any of those points, by definition, your function cannot have a derivative at that point. F prime of c for that particular c will not exist. That's case the first. Case the second and case the third are a little bit more involved, which is why I've got my buddy here, the calculator, to show us what's going to be happening. So this idea of a corner in the graph, there's kind of the classic example that we would use is our friend, the absolute value function. So I'm just going to do absolute value of x, and we'll just use, I'll change my graph window up a bit here. So we've got negative, we'll do negative 5 to 5. So negative 5, 5. That should be a 5. There we go. All right. Now let's look at the graph of this thing. You probably already knew what the graph of the absolute value function looked like. The classic V for victory, kind of look here. That really is this corner right here where there's kind of a jagged switch in what's happening. Up until we get to the origin, our tangent line slopes, if you imagine them, they really are just like that line that's leading down toward the origin. All of these tangent line slopes are, negative. If on the other side, you see the tangent line slopes are all positive because the line would be climbing as we move in the positive x direction. So we have this jagged transition from negative to positive tangent line slopes with no smooth transition in the middle. So so a corner in the graph is another scenario in which your function might not have a derivative at a given point. The last one, the vertical tangent line, is probably the least likely of the three to come up, but it can still happen. So I need to come back in and change my function up a bit for that to work out. So as it turns out, once again, let me come in here. Our friend, the cube root function, is actually sort of the classic demonstration of a vertical tangent line here. So let's see, as he slowly makes his way in, and we'll probably want to zoom in just a bit because once again, the origin is where things are kind of exciting. So let's change these windows up. So negative 1 to 1, negative 1 to 1. Draw the picture again. So yeah, no real tick marks or anything, but you can kind of see what's happening here. Sort of a trick I'll often give students for thinking about derivatives and tangent line slopes graphically is imagine that you've got hold up like a credit card or your driver's license or something to act as a line that's kind of touching the graph at those points. If you do that as you follow along here, you'll notice your slope is getting steeper and steeper and steeper and steeper and steeper and steeper and steeper, and then by the time we get to 0, the tangent line actually is the y-axis. It is this sheer vertical line. And coming back then all of a sudden it starts flattening out. But you shouldn't need me to tell you that a tangent line, or that a line that's vertical does not have a defined slope. So same thing. In that instance, a vertical tangent line, kind of ends up, barring there being a finite value for the limit because it would have to match up with the tangent line slope. And, there is no, there's no defined slope for that thing. So those kind of cover your bases. Sometimes people will associate this notion of a corner in the graph along with sort of that LHB not equal to RHB thing where your left and right hand limits disagree. The vertical tangent line sort of ends up being a case where it's more like the derivative values are like unbounded near the point because those tangent line slopes were in fact getting way steeper as we travel in either way here. So we got that. There's one last piece of sort of notation, bookkeeping, whatever you want to call it, that I want to address before we call it a section. Okay, this last thing, as you'll notice, some text has spontaneously appeared. Addresses just one last bit of like notation I'd like to mention. So we've talked about just now what happens if derivative does not exist. If the derivative does exist, in terms of language, we say that our function is differentiable at that point. So it's not like the end of the world in terms of if you get the words wrong here. But the act of taking a derivative, when we find a derivative for a function, we don't call it deriving. I know derivative makes you think that, but that's not what we do in our calculus classes. We don't derive, we differentiate. And a place where the derivative exists is a point at which our function is what we say is differentiable. And it's sort of like continuity. We'll talk about being differentiable on an interval. That means you're differentiable at all the points in the interval. I just didn't want that particular piece of terminology to catch anybody off guard. So that's kind of our intro to talking about derivatives and tangent line slopes. As promised, our next section, we're going to take a look at this from a different perspective. So, stay tuned.